Hi, welcome to module 50. So, we have hit half a century now. In this module, we will look at ripple carry adder. So, in the last module I said we will do this little thing that for 2's complement adder I said if there is an unsigned adder I will be able to make a 2's complement adder out of it by doing some extra logic. So, I am going to do how to design the ripple carry adder now or an unsigned adder now. So, this discussion is only about unsigned calculations, it is not about signed calculations. Let us look at adders and subtractors. These are the most basic operations in any digital computer, and in the homework and earlier also I have already talked about what a half adder is and what a full adder is. A half adder is a circuit which takes two input bits A and B and produces two output bits carry and sum. So, the carry and sum, if I take that as carry comma sum as a vector and if I interpret that in the unsigned form, that will give me the result of adding A to B. So, 1 plus 1 is number 2 and number 2 gives me carry equal to 1 and sum equals to 0. And if you look at the truth table here, so with respect to A and B, this truth table carry column is only A and B and the sum column is A XOR B. So, sum is A XOR B, carry is AB. I believe that you have already done this in your Verilog assignment from a few weeks ago. So, a half adder is a fairly simple circuit. You have a XOR gate and you have an AND gate, and remember this can add only 2 bits. A full adder is a circuit which can take 3 bits. You can take 3 bits A, B, C and it can give you 2 numbers C out and sum. Since these are 3 bits A, B and C, there is only 2 bits sum and 0. So, these are 3 numbers, at most it can be 3. So, 3 is 1 1, we can represent that using only 2 bits. So, this is carry out and this is sum. So, 0 plus 0 plus 0 is 0, so 0 is 0 0. Similarly, 1 plus 0 plus 1 is number 2, so that is 1 0, 1 1 1, 1 plus 1 is number 3, that is 1 1 and so on. If we go and do the Boolean minimization for that, you will see that sum is A XOR B XOR C and C out is AB plus AC plus BC. So, C out is actually the majority of the 3 and sum is the XOR of the 3. We have already talked about this at length at several occasions before. We did not call it full adder then, but now we know that it is a full adder. A full adder has sum which is XOR of all the 3 and carry out is majority of the 3 bits. So, you can do a slight simplification here. AB plus AC plus BC is the same as AB plus C times A plus B or C and A plus B. So, full adder is one of the implementations is directly taking this and implementing it like before. So, you take A and B, you XOR it and XOR that with C, so that is coming from here, take A XOR B XOR C, that is sum S, and this is the carry. So, we have sum and carry as it was before. And if you want to go and look at this full adder, the full adder I have used the suffix I, right, this AI, BI, CI which results in SI and CI plus 1. So, this SI and CI plus 1 are supposed to be in the intermediate stages. So, we have stages. At the ith stage we take the inputs AI and BI, take the carry I and the result should be sum I and carry I plus 1. So, there is another implementation that you can do for a full adder and that is actually using 2 half adders. You can take 2 half adders and connect them using this form. You take the sum from one of the ones and you take CI, give it as the inputs to. So, remember half adder can take only 2 inputs, right. So, this half adder is taking AI and BI and this half adder is taking the sum bit of AI and BI and CI. This is going as the inputs and the carry that is coming out of here and the carry that is coming out of here is OR together, that gives you CI plus 1. So, this is another way to do a full adder. Using 2 half adders you can do a full adder. The key thing is that as I mentioned before, at stage I there will be a carry, there would be a carry that is coming in from the right side, there are input bits that are coming in from the current stage, it may give you a sum and a carry out, right. So, we have already discussed this when we looked at addition of numbers and so on. Right. Let us look at how to analyze the performance of a full adder. So, this is a circuit that actually has a full two input NAND implementation of the complete thing that we have seen so far. So, it is actually, you look at this picture. So, there is an XOR gate, there is an AND gate, there is an XOR gate, there is an AND gate, and there is an OR gate. What if we implemented all of them using only NAND gates? So, that is this representation. So, this circuit is a half adder, and part of this is another half adder, and the carry out is also absorbing the OR here. So, this is a complete NAND representation of a 1 bit full adder. A 1 bit full adder is one which will take two inputs AI and BI along with the carry input CI. So, there are 3 inputs to the circuit, and it produces sum I and carry I plus 1. So, if you go and look at the delays in the circuit. So, this slide is about the performance of the full adder. Let us assume that all the NAND gates have 1 unit delay. Just to keep things simple, we will assume that all the NAND gates have 1 unit delay. What we will do is, we are going to look at analyzing the performance of this. So, let us look at the circuit here. So, this is supposed to be for a full adder. It takes 2 bits A and B, it takes a bit C, it gives sum, and it gives carry out. So, I have drawn this dashed line here. So, top of this is the first half adder, and below that is the other half adder. So, let us see how this whole thing works. So, if I take if I change A and B and C, let us say in one step I am changing A, B and C at time t equal to 0. So, the changes in A and B will have to go through at least 3 NAND gate delays for this wire to change, right. You already know how to analyze delays, right. So, if I start from here, it is at least 1 unit here, 2 unit here, 3 unit here for this path. If I start from A, 1, 2, 3 on this path also. If I start from B, again 1, 2, 3, 1, 2, 3 and so on. So, there are 4 paths starting from A and B ending in this wire, or actually here. So, ending in this wire. So, this takes 3 gate delays, right. So, that is what is written as blue here. The blue one is 3 gate delays. Now, if you go and look at this path, this has taken only 1 gate delay, that is going to the next stage circuit, right. It is going to the next stage. Now, let us see the next path. If I go and look at this path from here, let us say the inputs settle down at some point here. If I go and look at what is the delay here, then it goes through 1 plus 2 NAND gates. So, that is this path here. So, starting from AB to change C out, you need 3 gate delays plus 2 gate delays or 5 gate delays if I go through from AB to this one. So, any change in AB may take 5 gate delays for C out to change. So, however, C out is also taking in from C. So, let us see what happens to that. So, C is coming from here, it goes through 1 gate delay and another 2 gate delays. So, the longest path or the critical path is coming from A or B through this NAND network, coming in through this and through these two finally to C out. So, a change in A or B will result in at least 5 units of delay to change C out, but a change in C, it requires only 2 units of delay. So, if I have ABC at time t equal to 0, we can expect at 5 gate delay time C out will settle down. And if you go and look at sum, this gets settled down at 3, this was available at 0 itself. So, this input is available at 3 time units and this is available at 0, and there are 3 gate delays here. So, sum will settle down at 6 time units. So, in a single full adder, if I give A, B and C at time t equal to 0, in t equal to 5 gate delays C out will settle down, and t equal to 6 gate delays sum will settle down. So, the carry gets generated faster than the sum, and that is useful. We will come to that in a little while, right. The carry is getting generated faster than the sum. And finally, this last path is C going in directly through this and so on, right, that is only 2 units of delay. So anyway, the green path is not so interesting. The blue one followed by the orange one gives me the delay from change in input ABC to change in output C out. Then the blue line followed by the orange line, this light orange one is change in ABC resulting in change of sum. Change of C, however, is not a big deal, it is going through fewer gate delays anyway. Right. So now let us get into ripple carry adder. This is also called carry ripple adder in a few books. So you can implement a 4-bit binary adder by cascading 4 1-bit full adders. So let us see the inputs and outputs. The inputs are A3, A2, A1, A0, B3, B2, B1, B0, and C in is if there is any input to the carry to the ripple carry adder, you can give that, otherwise you can make it 0, and the result would be sum S3, S2, S1, S0 and a C out called S4. These will be the inputs and outputs. Let us see how this will be built. You take a full adder and you give A0, B0 to it. If there is a carry input, you give C0. If there is no carry input, you put a 0 here. This will give you sum naught and a carry 1. This carry goes as the next stage carry. This is what we do in decimal addition also, right. So if I have the ones, if I in the ones position, if I add 2 numbers, the carry from that will go to the tens stage. So if I in the 10th stage, whatever carry comes out will go to the 100th stage and so on. So imagine this as zeros, ones. So this is ones. So in decimal this would have been ones, tens, hundreds and thousands. Here it would be ones, twos, fours and eights. Those are the 4 stages. So this C1 and A1 and B1 will change S1 and C2. Then when S2 comes, A2 and B2 along with C2 will result in S2 and C3 and so on. So the key thing that you have to remember here is there is something called rippling of carry. So the carry that is generated from C1 may go and change the values for S1 and C2. C2 in turn may go and change the value for S2 and C3, which in turn may change the value of S3 and C4 and so on, right. So the carry that is generated from this rightmost stage may ripple through the rest of the circuit and may result in a change of C4. So imagine if I added 0001 to 1111, right. So A3, A2, A1, A0 would have all been ones and B3, B2, B1, B0 would be 0001. Let us say C0 is 0. So all these are ones, A is 1 and B0 alone is 1. So A0 and B0 will result in a sum of 0 and a carry of 1. That one here is coming now, that will flip this sum bit and change the carry bit, which will in turn flip this bit and generate a carry bit, which will in turn flip this bit and generate a bit here. The result will be 1 followed by 4 zeros. So that carry generated from here rippled through to all the way here, and there is a reason why we are looking at this circuit. The delay that you get from this circuit is quite long. So let us see what the delay is. So if I go and look at the internal diagram, so this is an minus 1, this is bn minus 1. Let us say there is a stage A2, B2 and there are other stages which are not shown, A1, B1, A0, B0 and so on. Let us see what is the longest path in the circuit or the critical path in the circuit. If you go and look at the critical path, right, let us say all the inputs are given simultaneously, all the bits A's and B's are given in one go, right. You will see that at time unit 3 it will have passed through the first adder, and in time unit 6 Sn minus 1 all the way to S0 would get some intermediate values. So everything from Sn minus 1 to S0 would get some values at time unit 6. However, at time unit 5 we get C1 which is coming through. This C1 can potentially change both sum and carry, right. So this came in through a delay of 2, so 3 plus 2 is 5, and if you look at this path, right, this is already coming at 5 units, this would have settled down at 3 units. So this is waiting, 5 units plus 2 units is 7 gate delays. At 7 gate delays, C2 will stabilize, C2 will not change anymore. So C2 is stabilizing at 7 units, this first half adder's output will stabilize at 3 units itself. So 7 plus 2 more NAND gates, so this is, we are talking about these NAND gates, these 2 NAND gates. So if this comes at 7 units and if this is settled at 3, at 9 this will get settled down. If this comes at 9 and if this input is settled at 3, this will come at 11 and so on. That is what we are looking at. So at 7, if this settles at 7, after 2 time units this will get settled down, after 2 time units the next stage will get settled down and so on, and every stage will settle down in the next 2 time units and so on. So overall, if you look at the calculations, so sum, if you look at it, so this path, this will take 3 plus 3 which is 6 time units, then this got settled at 5, so this will settle at 5 plus 3 which is 8, this will settle at 7 plus 3 which is 10, this will settle at whatever Cn minus 1 times something plus 3, so that will be the time at which it will settle down. So the worst case propagation delay for some term, so sum will come the last, Sn minus 1 will be the very last bit that will come out, and if you look at the path, then the longest path will be this one going through this set of carries all the way to this A0 B0, that will be the longest path. You can see that this carry chain or ripple carry, so a carry that is changing may eventually come and change here, and from there it will take 3 time units for Sn minus 1 to settle down. So the worst case propagation delay for sum in terms of 2 input NAND gates is given by 5 time units, which is in the very first stage itself. So the very first stage, this carry will come out at 5 plus I equals 1 to n minus 2, 2, that is through the carry logic. So this summation is because of the carry logic. This is the delay taken for the very first carry to be generated, C1 to be generated. This is the delay for Cn minus 1 to be generated. So I equal to 1 to n minus 2 times 2, right. So we are adding so many times 2, this is 2 gate delays of NAND gate, that is because of generating the Cn minus 1. But once Cn minus 1 is generated, you still need 3 more time units to settle Sn minus 1. So T sum is 2n plus 4. So where n is the number of stages and 2n plus 4 is the number of gate delays in terms of 2 input NAND gates that we require for this one. So the worst case propagation delay for carry output, however, is delay for Cn minus 1 plus 2, right, or it is actually 1 unit less than 2n plus 4. So you still need to generate Cn minus 1. To generate Cn minus 1, it is this factor plus 5, but this path only has 2 NAND gates, so instead of adding 3, we will add only 2, that will be 2n plus 3. So both of them, as you keep widening the width of the addition operation that you want, you will see that implementing using ripple carry adder is increasing linearly with respect to the size of the adder. So that is the final bullet. The propagation delay for an n bit ripple carry adder is linear in terms of the number of stages. This big O of n means this is a function, we do not have to say what that function is, but the function is growing linearly with respect to n. So a 1 bit adder may take some time unit. If I want to do two inputs, it will depend on this number 2, right. If I want to add 2 5 bit numbers, right, it is going to be a function of n, it is going to be a function of 5, 6 and 7 and so on. If you plot the delays for different n, you will see that they are in a line, that is why it is order of n, right. So ripple carry adder, if I want to make a bigger and bigger adder, the delay increases, proportionally with respect to the number of bits. So one final thing that I want you to think about is the carry that is coming out here, right, has an interesting property. If I have a 4 bit ripple carry adder and let us say I have another 4 bit ripple carry adder, I can take the carry out that is coming from one stage and given as C0 for the next stage, you can make a 8 bit adder out of that, right. You can take 2 n bit adders and attach them back to back and you can get a 2n bit adder. So that is a very interesting property of ripple carry adder. So this is one of the few circuits where you can take two circuits and put them together, and without doing any extra work you can actually get a bigger operation done. So I want you to do these as exercises. Design a signed comparator for comparing two 4-bit ones complement numbers A and B. So you are given two numbers A and B, the numbers are already in ones complement format, compare and give 1 or 0. If A is greater than B, give 1, if it is A is equal to B or A is less than B, give 0. Similarly do that for 2's complement. And finally design a circuit where you have a 2's complement number and you are given x, you have to give modulo of x. If the number is positive, it should return the number directly. If the number is negative, it should give me the absolute value of the number. So go and design circuits for this. So to do this, don't think in terms of gates, think in terms of the additions and subtractions and all these things that we have done so far, right? Think in terms of that. So use all the properties as, so the very first bit, if it's a 1 in 2's complement or in 1's complement, the number is negative. Use all of that information and see whether you can come up with circuits which can use adders to do this comparator and this absolute value generator. So this brings me to the end of module 50. In the next module we will, so what we will have to look at is we still have to look at multipliers. So we have adders now. With adders you know how to do subtractors. We will look at multipliers. Dividers are beyond the scope of this course. Dividers take a lot more work, and this is not something that we can do easily in a undergraduate second year level of course. I suggest that if you are interested in dividers, you go and read up material that is out there. So thank you, and I will see you in module 51. Bye bye.